Hi, I'm Dave Kassler, KE0OG, and here today to talk about WSPR. WSPR is the weak signal propagation reporter covered in a previous Ask Dave video that talked a lot about the theory. And one of the things that talked about in there was the ability to make a small device that was a QRP transmitter that would transmit the WSPR signal from your location. And you could, from anywhere in the world where these are broadcast, you can pick up who is hearing them on WSPRnet.org. That's WSPRnet.org, and there's a map facility there, and we'll see that. Now, what this video about is building the transmitter kit. It comes from an organization called QSL-Labs. Is that right? It's not right at all. QRP-Labs. And QRP-Labs has a series of kits, and I've looked at them before and have always been a little put off by not being quite able to figure out what all I would need to buy to get a complete kit. Well, Michael Lloyd, a very loyal viewer and a frequent commenter, decided after I did a video about kit building that I needed to get better at it. So he sent me a bunch of little kits to try, and one of them was the kit for this particular WSPR transmitter. It's not a transceiver, it's a transmitter. And this, I decided to build it for 30 meters. He gave me band kits for several others. I thought I'd build it for 30 meters. And it is from a whole bunch of parts and pieces. Now, here is the thing. I've looked at doing this before, but the issue has been that I look at the website and can't figure out what I need to build a complete kit. It's all an option this, option that, option so on. I'm going, oh, okay, what collection of these do I need to actually make something? It's not the only website that's like that. The Elecraft website is very much like that too. If you've ever gone to the Elecraft website and say, okay, I want to get an Elecraft K3S transceiver, good luck. You've got to sit down there and get a PhD in studying that website to figure out what you need, because going in there and saying, okay, I'll buy a radio, it's like going into a car dealership and saying, I'd like that car. And then the salesman say, that's great. Would you like tires with that? And it's kind of like that for this particular website. Anyway, he sorted through that for me, and I spent quite a bit of time doing it too. And he sent me the kits to build. And this video is about building the one for WSPR and testing it and making it work. It's a little 300 milliwatt, that's less than a watt, transceiver on WSPR, and it's a pretty amazing little device. So let's dig in. But that's the transmitter kit. However, that won't work unless you plug in the synthesizer kit that has got an IC in here that will create a very nice transmit signal for them. It actually creates a square wave, but it gets rounded down by filters until it looks like a sine wave when it goes out here. Now, of course, if you're going to have that, you need to have a GPS receiver here. This is actually a GPS receiver. Okay, it keeps this in sync so that it is as accurate as the GPS receiver, okay? Now, I mentioned that this has to be filtered a little bit, so you've got all these band filters. Basically, if you want to use, say, the 30-meter band, what you do is you plug this filter into here. And so that doesn't tell the oscillator to do much different so much as to get the harmonics out. This is actually what one of the little filters will look like, all plug in. Okay, so he's also sent along some things to make connectors. These are little DC to DC converters that will take the 9 volts down to 5 volts, which this thing needs 5 volts. Here's the cable to go from the GPS receiver to this. And he sent a case, a very nice metal case here that's got all kinds of buttons and things like that. And some heat shrink tubing over here. Okay. The instructions are on the web page in several different files. So you have to download a lot of them. And I've decided the first thing I'm going to construct, since you kind of construct from the bottom up, is the synthesizer module. Okay? So we'll take that and see if maybe this evening I can't actually get that thing up. And I suppose we could use the oscilloscope to see if it works. So, shall we get going? I'm illustrating two things that turned out to be crucial to putting the kit together. One is that light up there that has a great big magnifying glass in it. My 65-year-old eyes don't do too well. I'm putting a jumper in at this point. The other thing that's critical is that device there that holds the circuit board in one position while you are doing something, and then with it held there, you can flip it up and over and around, so you can get at the back to solder it, look at the front, and so on, just like that. Very, very handy device. This is the light that I'm using up there, and now I've gotten to the point where I've attached the display board, and this is to the main transmitter. The synthesizer kit has already been built. Note that all of the spacers are included with the kit, and what we're doing now is just getting all the various headers and things like that put in place. Interestingly, there aren't that many pieces to any part of the kit, but they all do need to be mounted with care, and the quarters for building them are pretty small. I would not rate this as a beginner's kit, but hey, you never know. If you've got a good Elmer, give it a try. Right at this point, I'm soldering the connector that goes between the display board and the transmitter board. They suggest that I assemble it here, put it together, do the soldering on each one of those little pins quickly but properly, and do that on the display board also. And then the two boards will still pull apart because that connector's been put in place, and the connector will be perfectly aligned because it was soldered sitting in a position it was perfectly aligned. Okay, this is the point where I've actually built the kit. It's finished. I'm going to show you the different parts of it, but it has stopped working for some reason, so we're just going to take it apart until we find out what doesn't work. I should point out that it has to have the setup programmed in, and there it's supposed to be working, but it is not. So let's go back now to the real-time narration. The longitude, okay, and here comes the altitude in meters. That's almost exactly 7,000 feet. And then the GPS word, which is missing the 3D right there. The little heart is a heartbeat. The GPS sends out a pulse every 1 second exactly, and so the system here will calibrate itself to exactly the correct time, which is very good for whisper. The 26, and that greater than symbol really is more of an arrow. The 26 means how many minutes after the hour it will next transmit. See right here, it's 22 minutes after the hour. It'll transmit 26. Now these buttons here are used for programming. They actually match a couple buttons that are on the board itself and are brought out to the front panel. One thing I don't like about these buttons is they really do need a debounce routine in the software. So you just saw it skip something there because I hadn't pushed the button quite definitively enough, and it took it as 2 pushes. There's standard software debounce things you can do, or you can get buttons that don't have that sort of a problem. And then you close it off with that, and it goes back to what it's doing. Right now it's calibrating. It's calibrating its internal oscillator, little SI 5153 in there against the GPS. This calibration takes a couple minutes to go all the way through, and the longer it takes, the finer it can get it, and it will adjust the internal clock. A little thing about what's on the back, these are where the GPS connects right here, power, and I put an SO239 on this. All of my in-check stuff are SO239, and this is a dummy load that consists of a single 50 ohm resistor. Okay, so that's the dummy load. Inside here, this is a little 12 volt to 5 volt converter, and it's perfectly flat on the underside. It uses surface mount components. This I got, it was already built, so I put a piece of packing tape in here, and then on the back of this put double-sided tape, just regular office style double-sided tape, and that thing's not going anywhere. Now you see in here several boards. This one on the front is the display board, okay, and then there's a header, and then the board that actually does the work, and a little board up here that provides the local oscillator that is synchronized to the GPS. And here's a little low-pass filter. Now it's interesting the way this thing works. We're getting closer here. I'm going to clip on some leads. This is to the oscilloscope. We're going to see if this thing works. It was not a minute ago. Okay, this is connected to a dummy load now, so we're just observing with high impedance there what's going on inside. Again, it's not a receiver. It is a transmitter. It's a beacon. Transmits only. Now the way this thing works is this little local oscillator here. There's a 27 megahertz crystal, and buried way down inside there is a chip that is surface mounted onto there. It comes surface mounted in the kit, and that puts out a stream of square waves. Well, square waves are a combination of it appears to be transmitting right here. Let's see if we can get anything on this oscilloscope. Yeah, I'm not getting the nice clear wave I was getting out of there. Okay, back to the square wave. The thing puts out square waves at the frequency, and then it goes through a band pass filter, and you can get these for different bands and plug them in, or if you're really into this, you can get a relay board that you can plug in 5 bands, and so it'll switch frequencies back and forth. You need a very broadband antenna to do that, however. The bandpass filter right here, for example, if this is putting out on 10 megahertz a square wave, and this is a bandpass filter, so it allows things around 10 megahertz through. Remember that on square waves you get the odd harmonics. An odd harmonic would be the third, would be 30 megahertz. So from 10 to 30 megahertz, if you filter out everything above that, you're going to get the fundamental component of this, which is a sine wave coming out of the thing, a very nice sine wave. Now, if the square wave is not perfect, then that means there will be issues doing that. You could get other stuff slipping through, but if the square wave is pretty close to perfect, then you can filter out anything that's not part of the sine wave. It's pretty cool the way it works. Okay, let's take the thing apart and look at the different parts and how they went together. Well, we get a nice picture here of the display board. Comes complete except for this right here, which has little pins sticking out the back, and so that has to be soldered there, and the way to do it so everything lines up is to get the main board right here aligned. See, with the little pins right there, and plug this in. I'm having trouble. There we go. Okay, so you solder these. They're held apart by the spacers. Then you solder these, and you can see there's just a little bit of a gap down here that you can just see light through, and it's just because of the size of the spacers there. That way everything fits very nicely. So let's plug in the power at 12 volts. And then this next part here is the GPS receiver, which is separate. The reason it's separate is because you put it inside the case, you lose your signal. I've got everything set up with this PL259 antenna going into the SO239 that I've put there. Okay, what we're going to do now is hook the parts of the board back up and wait for it to transmit. Okay, this is the little synthesizer board. That little chip right there, you can see it's surface mounted there and there. That's the actual synthesizer. There's a 27 megahertz crystal that this uses to run what's inside here, and then depending on what's coming in terms of orders for the pins, it will cause this thing to put out a square wave at a precise frequency down to the hertz, assuming the crystal is perfect, right onto the board in the way it shows, making sure we've got pins lined up on both sides. And there we go. We've got the thing on. Now, I made a mistake when I put this thing together. It showed in the instructions like I was supposed to actually hook wires to these spots. But actually, you get later into the instructions and it says, no, put a header in, and then you can create a little something that'll plug into the header. And it includes quite a large supply of these things. These things can be broken to any length that you want in terms of number of pins. This right here is the 30-meter bandpass filter, and you notice that I wasn't exactly always the best putting things together. Now note, this is different from what you see on the website. This has just two of these horrid toroids, okay, two tuning capacitors, and there's an inside and an out, and this is the out down here, okay. Now the reason this is important is because this will determine which frequencies can actually go out. Now note that to change the frequency you have to change the bandpass filter, and the programming or the instructions on the thing too have to match that. You have to put the right frequency, the whisper frequency that you want in there. So this will plug right in. The way it says to test these, if you don't have a signal generator, which I don't, that goes up that high, is to just put this in line with the receiver, find a signal that's strong, and tune this. Well, let's look now at the, that says right there, out. So we'll put that in the board here, where it says out. Goes down here. Again, we make sure that all the pins line up and it goes in here, okay? Now this over here on the main board is where the oscillator, GPS oscillator comes in. This potentiometer right here changes the luminescence on the screen so you can see things. It's a very sensitive adjustment. And then this adjustment down here is the drive to the final amplifier. I opted to take the one, and I at one point into a dummy load measured 350 milliwatts, which was very nice. But when I put it on a real transmitter, or when I put it onto a real antenna, I got kind of different results. So Now that it's stopped working, I've got to figure out. Everything works in terms of the display. And here's the power out right here. Okay, so we can start tracing it from the transistor through the filter and on out. There really should be coax connected there at this, and actually I should have put a header there. So stupidly I did not. I think what I may have to do is try to pull those and then see if I can force a header in there. And the same over here for the buttons. They should have had, and it did not mention this at the right time, there should have been, put a header here so that it could have hooked that to header, would have made it much easier. Okay, so what we're going to try and do is poke through here with the oscilloscope to see what isn't working and why. And for example, right coming out here, there should be an input over here, which should be a square wave, and coming out of this should be a sine wave. Okay, and we'll see if that's true. Now I've got all of these things hardwired to things on the case, and I don't really want to take everything off the case. So we're 47 minutes after the hour. That is the correct time in UTC. And at 56 minutes after the hour is when it is next going to transmit. Okay, so I'm just going to put this in here to keep that from shorting to anything. Well, that's working now. What happened is that the chip on here, the main chip, decided that it wanted to reset itself. If it first comes up the first time it's used, it's got a diagnostic on the front of it, and then you have to push the buttons and program it. And there's a big, long list of things that have to be programmed. Different frequencies, whether or not it uses the GPS, this mode, that mode, checksums, blah, 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 and I would have had absolutely no idea what to do with them, except this sheet of paper came with it. It was, I guess you would call, a suggested programming list. And then I had to modify this because as it's set up, it's for like the relay board that has 5 different bands. Say, okay, it has stopped sending now, and it is going through, I'm going to take this off of here, like that. And it's going through its calibration routine after it's just sent, okay? And it takes 240 seconds to do that. So that's 60 times 4. So it takes 4 minutes, and it's going to take that little heartbeat from the GPS and calibrate itself over and over again. So that was to the dummy antenna. I'm going to connect up the real antenna here. And this is the loop, the MFJ 1788 loop, which I've previously tuned to be exactly on the right frequency. So there's also something going on with my vertical antenna, so that gives me lots of things to fix. See, here we are, we're still going through the calibrate run on this thing. Great. Little meter measuring the number of amps while transmitting. 0.31 amps, well, 310 milliamps while transmitting. So let's see what it goes down to here when we get done sending this particular transmission, which by the way looks great. I should add that this is going through on the 12 volt side prior to the little regulator here. So the way these regulators work, it drops the voltage, the current stays the same going through it, so we get power lost in that regulator right there. Okay, this is the little GPS board that comes with it. This is the patch antenna. It's about 1 inch square against a ground plane underneath it, about 3 inches square. Okay. This right here, this surface mount device is the receiver. That comes pre-mounted. This does not, but this does come pre-mounted. Then here are the electronics to read it out. That right there, the red just indicates it's on. The green is a pulse per second. The rise of the pulse is coincident with the rise of the signal that is being sent down there. Okay? Yeah, we just lost the GPS signal because we've got it upside down here. Okay. There it comes back again, and you can see this right here is a word that is being put together by this, a digital word that has detailed information about the time and location. Again, we're using this primarily for the time, but this will compute the grid square, the Maidenhead grid square, which where I am is a DM68. And I'm going to show you a little bit about grid squares and how they're not very good for actually locating things, but they'll give you a general idea of where something is. This was pretty easy to construct in here. There's no toroids to wind or anything like that. And Michael was very kind to put a cable together for me that comes right into this board and picks things up. So that's GPS. I'd like to end with just a little bit more about Whisper and what this particular kit does. It's not only for Whisper. We see it is for Whisper, the weak signal propagation reporter. It will also do a weak signal mode called very, very slow Morse code, QRSS. The QRS signal means please slow down. So QRSS is very slow code. And if it takes like, a minute to send half a character, you can often pick it out through very high noise. Frequency shift keyed CW mode, dual frequency CW, Whisper, of course, Opera, PI4 beacons, another kind of Whisper 15, okay, with 15-minute frames, JT9, 5 different varieties, Hellschreiber even, which is sort of an image mode, just plain old-fashioned CW and plain old-fashioned frequency shift keyed, and then you can even send customized patterns if you want to. It uses the 5351 synthesizer module, which is the one I showed you. It's a surface-mounted device, but it's pre-mounted for you. There are plug-in low-pass filter boards that you can get to run even down into the new bands, which haven't been turned on, the extremely low frequency, all the way up to 6 meter. There's, of course, the display. You can set up the way you want it. You can connect it for GPS to lock the frequency. Timing, location is given there. In some modes, you can actually send out the location. You don't need a PC with this to send Whisper. Again, this is a transmitter only. The Maidenhead locator can be generated from GPS derived latitude and longitude, which I do. Mine is DM68, and I'm going to show you in a minute just what that means. Selectable frame size, It's got all different kinds of things. You can add more power output transistors. This is about what I'm getting right here, 1/4 of a watt. Okay, just to show you how big a grid square is. The grid square, the longer the number of letters in the indicator here, the closer you get. So at the 4 level, FN, and then in FN, in square 20, this is what it is. This is what you get for a 4-level Maidenhead grid square. Note that this covers all the way from New York to Philadelphia. It is a big chunk of territory. Now, in my case, I live in grid square DM68, which is what this thing will send out. It will locate me somewhere within this particular quadrant. It's huge. I happen to be located way down here near Ridgeway, halfway between Montrose and Ouray. And this particular grid square is just huge. It goes all the way over the divide of the Rockies over to the other side. Now, if I put the CG on the end, let me just go back for a moment to this one. CG would be about that area right there. Okay, so we'll just go over to CG, and you can see where I am, actually down to the street level. And this still covers a pretty good-sized area, several square miles, but it gets much closer. I thought you might enjoy just seeing how close I live to the edge. The edge of DM68CG happens to be the back fence out behind us. This fence runs along a line that has geodetic meaning, so it does coincide right there. My antenna, my vertical, is right in here with the radial field out like this. I have the loop antenna out about here. This is the transmitting loop, and then the receive loop is right there. So we've got about an acre out here in paradise. Okay, I'll call it that. Now the question is, when you put the transmitter on the air, does anybody else hear it? And those who do hear these transmissions send them up to the internet to a place called WSPR net. WSPR, let's see, I'll get it for you. Whispernet.org, I think it is. And these are all the stations that heard me in a 24-hour period. So a couple in Australia, one in Brazil, and a whole bunch in the United States. Let's just take a closer look at the United States. Now, again, the antenna I'm using is the transmitting loop from MFJ, the 1788. And note that it is oriented so that its null is due north and due south. And you can kind of see that here. I'm not getting signals from due north, due south. I've got it that way because there's just not really very many people along that line. Most of the East Coast, I'm picking up West Coast. And it may not look like it, but going out to Australia from here, we don't go south, we go nearly west. So that's a quick overview of Whisper, what it does, and it shows that this particular transmitter works. Signal to Australia, 1/4 watt. Well, thanks so much for watching. It's fun to talk about Whisper and what can be done with it. It's one of the more exotic of the digital modes, and here we've seen a way to have something set up just for Whisper. I plan to put up a 30-meter antenna that I can devote to this all the time. If I put it on the loop, the problem is that the temperature changes day to night, and so the dimensions of the capacitor and the loop change, which are enough to throw it out of tune. So it's going to have to be something more general like a dipole. Thanks again for watching. Please click like. Please also subscribe and click on the bell so you get notifications of future videos. Use both feet when walking. Check out the tip jar and Patreon. Until next time, 73.